This is problem 6 on the exam review worksheet, and in this problem we'll be designing a state diagram for a sequential circuit with one input U and one input R. When the input sequence is 1, 0, 1 on the 3 preceding clock cycles, then the next clock cycle R is 1. Then on the next clock cycle R is 1, otherwise R is 0. And we will be looking for overlapping sequences because for this problem you can have those. Also, this one is a Moore machine. Let's see how it's different from a Mealy machine. So on problem 5 we had a Mealy machine, and this is what problem 5 looked like. Whoops, that's not what problem, well it is, but not what I meant. Okay, so problem 5 was, first of all, it told us it was a Mealy circuit, so we knew that. And it says that when the input sequence is 1, 1, 0 on 3 consecutive clock cycles, then P is 1 during the cycle in which the sequence is detected. So that's what makes it a Mealy machine. It's during the cycle in which the sequence is detected, as opposed to the one we're doing right now, which is if it was in the 3 preceding clock cycles, then on the next clock cycle R is 1. And that's going to make it a Moore machine. Okay, so let's think about what our possible states are that would help us get towards the sequence that we are looking for. So let's just look at examples. Let's say we had the sequence 1, 0, 1, 0, 1, 1, 1, 0, 0, 1. And let's see when we detect our pattern of 1, 0, 1. So here we have a 1, and that's getting us on our way to 1, 0, 1. And then a 0 is still getting us on our way, and then a 1. And so now we have a sequence of 1, 0, 1. So that's, we can detect that. Then we have a 0, and look, we can use this 1, and it's getting us 1, 0 towards our sequence we're looking for, and then we have 1, 0, 1. So this 1 overlaps this 101 and this 101. So now after this one, I get a 1, and I'm only at the first state that's getting us towards our desired goal of 1, 0, 1. And then I get another 1, and again, I just am at the first state where I have a 1, not getting further to the goal. Then I get a 0, and now 1, 0 is getting us further to the goal of 1, 0, 1. But then on the next clock cycle I get a 0, and now I got zipped because I'm not anywhere that will get me towards the sequence of 1, 0, 1. And then I get a 1, and so I'm at the earliest state that gives me something towards the sequence. So the different states that we will have are got zip, and notice that happened when we had a 0 followed by a 0. If we had a 0 that came after a 1, that would not be got zip because that would be getting us towards our sequence. Now when we have our first number, that would be got 1. When we have our second number, that would be got 101, 10. And our third state that helps us get anywhere is our actual answer, 1, 0, 1. So those are going to be the 4 states that we have. Notice that in this problem we have 4 states, whereas when we did the Moore machine, we only had 3 states. Let's look at that. So here was the Moore machine we did, and we had 3 states. 1, 1, 0 was not a separate state in our machine, because once we had 1, 1, then on the next output we'd output 1, but then we didn't have to have a separate state for it. But for the Moore machine we do. So here are, let's go ahead and draw our states. And with a Moore machine, the output depends only on the state that you're in. So we can say what the output is on each state. So if we got zip, then our output is 0. If we got 1 and just a 1, our output is 0. If we got 1, 0, then our output is still 0. That's an R equals 0. And then if we got 101, then our output is 1. So on a Moore machine, you put your output with your state because the output depends only on the state that you're in. So let's say we got zip. Either we're at the beginning of our sequence and we got a 0, or we're somewhere in the middle of our sequence and we got 2 zeros in a row. So that would be got zip. So if we get another 0, we're right back where we started. So that's if you get a 0. If we get a 1, that 1 could be the start of a sequence 1, 0, 1. So that would be that we got 1. Now let's say we've got our 1, and let's say our next input is a 1. Well, that doesn't get us any further to 1, 0, 1, but it also doesn't move us back because we still have a 1. And so we're still at got 1. So we're at got 1, and let's say we get a 0. Well, now we're further along on our sequence of 1, 0, 1. So we got 1, 0. Okay, but let's say we got 1. Oh, we already did that one. Okay, so now we're at got 1, 0. If we got 1, 0 and we get another 0, well, now we don't have anything. So we go back to got zip. So that's if we got a 0. But if, on the other hand, we have a 1, 0 and we get a 1, well, now that's the state where the output will be 1. So if we get a 1, we go to got 0, 1, and our output will be a 1. Now, after we have a 1, 0, 1, if we get a 0, then we're back to the state that is got 1, 0. If we are at 101, so we're at 101, and we get a 1, then we're at the state got 1. And that is our Moore machine for a sequential circuit that will detect the sequence 101 on the 3 preceding clock cycles.